Okay, Assalamualaikum. So basically this video is on chapter 1.5, but I am so sorry. I missed up some points in the chapter 1.4, so I continue inside this video with the chapter 1.4 first, and then we go to chapter 1.5. So for the continuation from the PID control that I teach inside the video 1.4, okay, feedback control decide is by solving an equation based on difference between the control variable and set points. So this one is clear, right? So the feedback controller is used to cater the problem whereby control variable is deviate from its set point. Okay, so for the feedback control, the main objective is to reduce the error signal to zero. That error is come from the set point minus with the measured variable from the control variable. Okay, so basically this is the equation to calculate the error. Okay, basically the set point is set is the input of our controller, whereby the control variable is measured, and then these two is the difference between these two is it will become our error signal. So basically, if the question asking you to find the error signal, you can use this formula. Okay, finish for chapter 1.4. Now we move to chapter 1.5, which is operation and response of control system. Okay, inside this 1.5 chapter, we will cover on the open loop step response, three-term controller, the characteristic of P, I, and D controllers. Okay, I will show you the type of response of each of the controllers after this. Okay, so basically open loop step response is the testing that we do by manipulate the opening of finite element for manipulated variable. So in other words is we regulate the manipulated variable to see the effect on the process variable. Okay, so this is one example for the self-regulated system. So for your information, self-regulated system is the system that will reach a steady state. Steady state means it will reach a certain value of constants at certain time without having any controllers. So in here, the rise time is about 1 second. We can see here the rise time is about 1 second. After this, I will show the graphical figure. What is the rise time, what is the settling time, what is the overshoot and steady state error. So, and the settling time is about 1.5 seconds. So from this point, the system start to reach its constant. That's why we call it as a settling time. So let's design a controller that will reduce the rise time, reduce the settling time, and eliminate the steady state error. So in here we can see that the rise time is quite higher, and the settling time is also higher, and there is a steady state error inside this open loop system. So in order to cater this problem, we have to install the controller and make it the closed loop system. Okay, so basically the rise time is between this point to this point. So this is the rise time. So for the settling time is the point where it start to reach the constant value. The system start to reach the constant value. Here we can see here, this is the first point, it will start to reach the constant value. Okay, meanwhile the steady state error is the error of the control variables deviate from its set point. it's basically the one that I teach you in the first slide, the set point minus with the control variable, the measured control variable. So that one is a steady state error. Okay, so overshoot, normally some system is highly dynamic and fluctuate. So we have a noise, and this trend basically is a instability of the system, and also we can call it as noise. And basically the peak, the maximum peak here, we can take it as a overshoot. Okay, so basically overshoot we can calculate by rate the value at this point and minus with the set point value, so we can have a overshoot value. Okay, so we have three terms of controller, which is proportional, integral, and derivative. So for proportional, we can they use the proportional gain. For the integral is integral gain. This k is a gain. For the derivative is derivative gain. So this is the example of the response of the feedback control. Okay, basically this is the self-regulated system because they reach a constant value without having a controller. So without having a controller, they still can reach the steady state constant value, but it will not reach the set point. So after adding proportional control, that proportional control bring the response near approximate to the set point. Okay, normally the proportional control will not directly bring, will not successfully bring the control variable to its set points. There is some error, steady state error. So it can bring near to the set point, but not exactly on the set point. So that's why we have to install with the PI, and that PI will eliminate the steady state error and will push the system, the control variable to its set point. But this controller will produce some fluctuation, some noise, the instability. Okay, in order to cater this instability, the fluctuation, we need to install another type of controller, which is derivative controller into PI controller. And from here we can see that the fluctuation becomes smoother, right? And the response become what we call like the fluctuation becomes smoother, and the peak of the overshoot itself become lower, and it will reach the set points. Okay, so now I will explain one by one the response, the closed loop response for the now for the proportional control. Okay, here we can see basically this is the type of the response of the controllers, the closed loop controllers. So basically this is a flow system, and this is a level control system. Okay, basically the proportional control speed up the process response and reduce the offset. However, it increases the overshoot. So okay, from the figure that we see just now, the system with no control. Okay, basically when we install proportional, the system response, the process response will be speed up. That means it can reach set point, it will reach constants in the fastest way as compared to the system with no control. And then it will reduce the offset. Basically, offset is the deviation of the control variable to its set point. However, it increase overshoot. So this one here, we can see there is an overshoot, right? So proportional control will increase the overshoots. Okay, next, the controller gain can be adjusted to cause a quick change to the control valve upon a load disturbance or a change at the set point. So basically, if you want to adjust this response, or to make it to get a better response, basically you can adjust the controller gain. Okay, the method of adjusting the controller gain, we call it as a tuning. Okay, if the process response is within the quality limits, then the controller setting is considered acceptable. That means if we can see that the overshoot of the response is within the limits, the settling time is within the limit, the rise time is within the limit, the offset also within the limit, and then the tuning that we done before, which is the controller gain we adjust the controller gain, then the tuning value, the control setting is considered acceptable. Okay, lastly, for the proportional mode, controller output is a function of a change in error. So basically, if we in a proportional mode, if we change we tune the system, we tune the controller setting, the output of the controller itself, it will be the function of a change in the error from the deviation of the control variable to its set point. Okay, so in this system we can see that the controller gain for the proportional controller is around 300. So you can play around this value, you can increase up to how many you want, but bear in your mind, you need to see the trend, how the response is changed. If you increase the KP, and you have to see, is it stable, the response is stable, or is it become worse? So if the response become worse, you have to decrease the KP until certain limit. You have to see the response. Sometimes if you decrease too low, it will cause the system to fluctuate also. Okay, so basically we can see here, if we try to adjust the controller gain, so a high proportional gain, so if the controller gain for the proportional controller is high, large change in the controller output, so there is a large change of controller output, so that controller will ask the finite element to take an action in a large scale. If the proportional gain is too high, the system can become unstable, like what I'm saying before. If you increase the KP up to certain limit or beyond certain limit, the response will become unstable. So in here we can see, if we increase, if it's too high, this is too high, and then the system start to fluctuate, become unstable. In contrast, a small gain result in a small output response to a large input error and a less responsive or sensitive to controller. Okay, that means that if we use a small gain, here is small gain, it's high, too small. So small they result in a small output response. That means if there is any deviation of the control variable from the set point, it cannot cater. It cannot cater and cannot take a good action to make a correction for the final element. So if the proportional gain is too low, here too low, the control action may be too small when responding to the system disturbance. That means it's no use we use the proportional controller if the gain is too small, because they cannot take an action. So some controllers have a proportional band setting instead of controller gain. So normally we will use KC, controller gain, for the proportional modes. But some controllers, they will use a proportional band. So the proportional band's formula is 100% over with controller gain. Okay. So now I move to proportional integral control. So we have reduced the proportional gain KP because the integral controller also reduced the rise time and increased the overshoot as the proportional controller does. That means double effect. So this response represent the integral controller eliminated the steady state error. So from the previous response, right, we have an overshoot. By installing this integral controller, and we also have a higher rise time based on the response for the proportional controller just now, right? So by installing this integral controller, the rise time will be reduced. But still, we have a overshoot. This integral control cannot eliminate the overshoot of the system. It just eliminates the steady state error. The steady state error is the deviation of the control variable from the set point. Okay, so if we tune by increasing the integral gain, okay, the instability will be reduced, but the overshoot will be increased. Then if we increase the proportional gain, the system will start to fluctuate, become unstable here. Okay, basically to get the good response, we have to play around with this KC for the proportional and this TI for the integral. Okay, now we move to proportional derivative control. So this plot shows that derivative controller reduced both overshoot and the settling time and had a small effect on the rise time and the steady state error. We can see here, right, the rise time is from here, from here to here. From here to here, right? So as compared to the response for the PI and P just now, PD will reduce the rise time, and also the settling time reach fastest as compared to the PI and also P response. Basically, derivative control is used to reduce the magnitude of the overshoot produced by the integral component and improve the combined control process stability. Okay, so in here from the P just now, P proportional response just now, we can say that there is a high overshoot, right? So if when we install the derivative control, this derivative control manage to reduce the overshoots. Please do not compare with the PI. You need to compare this proportional derivative control with the proportional control in the first response that I show you just now. The first closed loop response that I showed you just now. Okay, so lastly, in order to eliminate 100% the overshoots, and to get the fast rust time, to eliminate the steady state error, we can add in derivative control to the proportional integral control. So from this response, we can say that the rise time, there is no rise time, right? Sorry, the rise time is fastest. So I think it's around here, from here, right? Okay. So there is no overshoot in here, and the system, the process, the control variable is reached its set point successfully. So there is no steady state error in here. Okay, so basically, the block diagram for this controller system is like this. So this Kp is represent proportional control, this Ti represent integral control, and this Td represent derivative control. So if the controller use all this kind of PID controller, then there is a value for this Kp, value for this Ti, and there is a value for this Td. So if you want to use only P, so there is no value for this one, there is no value input for this one. Only the controller setting for this one is input to the controller system. So if you want to, same goes if you want to use PI only, then you do not need to input the controller setting for this derivative term. So basically this is the figure of the controller system, proportional, integral, and derivative controller system. So I will explain in detail about the controller setting or tuning inside the chapter 1.6. Okay, thank you.